Hello everyone, welcome to the Interactive Immersive HQ. My name is Blake Heckerman, and I'm a new media artist and creative technologist based in Brooklyn, New York. I've worked all over the world on interactive installations and permanent exhibitions. And it is my pleasure to be here today and talk to you guys about number 2 in our series of simple GLSL techniques. This time we're going to be looking at quantization and specifically finding a way to pretty easily create a nice aspect correct quantization effect that you can use to create really nice pixelated effects and image overlays. So with that, let's jump into things and kind of take a look at where we're going today. First, you can see we have this kind of wavy quantization going on. We can turn that wavy net down so that we have just this static square quantization. By changing the pixelate parameter, you can change the size of those pixels. And if we make it really high, it's virtually like no quantization is there at all. And put it back at 50, you can see, we're back to some pretty chunky little blocks. So we're going to recreate this entire thing. I'll jump inside and we can take a look. You can see it's pretty simple. We're going to do all this from scratch. And so with that, I think we can just get going. So I will delete that. I will drop a base. I will call that base Quantize. Inside, we're going to drop down a movie file in to start. This can be any movie file in, of course. I'm going to use the Trillium because I like the Trillium. From here, we can drop down first actually a limit. And the limit, I'm going to backdrop real quick, and we're going to go into Quantize tab. We're going to turn the Quantize position value to floor. And if we change this from 0.1 to maybe like 0.05, you can see what's going on. And this is really the effect that we're going to recreate. What is this? This is quantizing the position of our lookup from whatever its decimal value is to some rounded value that will look up the color at whatever the rounded pixel is as opposed to the unrounded specific pixel. A good illustration of this effect in a one-dimensional setting can be seen here. So we can see you kind of have this curve, and at every point on the continuous curve, there's obviously some decimal values. And then you see the red line, which is the quantized curve. And that is, in this case, it looks like using the ceiling function to determine the integer value above whatever the actual continuous value is and returning that lowest integer above the actual value as the quantized result. And that gives us this stepwise red line, which is the quantization of said curve. So we're doing the same thing in 2 dimensions, and instead of having our curve here, we have our XY, or a UV map, which is from 0, 0 in this corner to 1, 1 in this corner. And instead of looking up at every decimal value between those two, we only look up every so often. So for example, maybe 0.01, 0.01, 0.02, 0.02, 0.01, 0.02, for example, and using that sampled value for all of the pixels in between the current sample and our last sample. So hopefully that makes sense. And the reason that we're going to do this in GLSL is twofold. One, we want to be able to use an aspect correct quantization function, returning nice squares instead of rectangles. Because if this limit was, for example, a square, and we used the aspect of the actual top itself, then we can see these square blocks. But that's not very helpful, because if we turn our position step to be very small, so that there's almost no quantization happening, our image is stretched. And we don't like that. So what I want to do is write a GLSL shader that's going to preserve the original input image and its aspect ratio, but still have nice square quantization blocks. And so for that, we're going to get into the GLSL portion of this tutorial. So before we get into it, I'm going to actually just copy this position step parameter of the limit, and I'm going to customize a parent component and recreate a parameter called position step, and that'll be a float, and it can go from 0.001 to, well, it can go up to 1 probably, and we can default it to 0.1, let's say. Actually, maybe I'll just make the max 0.5. And so now I'll right click, we can open my parent parameters, and I'll see I have that position step right there. Okay, now let's jump into our shader. So I will edit and find where my cursor window went. And then I'll put TouchDesigner on this side. Okay, so now we have a basic shader, and we can start to use this to create our quantization. And specifically, I'll just title, have a comment at the very top of my shader, aspect correct quantization. Just quantization. Okay, so as we had just talked about, what we need to do is first look up a color for the pixel in our shader based on the input image. And we can do that just by using this built-in first line and deleting that built-in second line. So now we have just copying our image over. Now if we go back to here, we want to do this again in the two-dimensional plane, which means for every decimal x and y, we're going to take the integer value, although it's not actually going to be an integer value, we're basically just going to round up our x and y coordinates to be a little bit higher than they actually are, and we'll take that sample for all of the xy coordinates between the last rounded value and the current rounded value. Those values will be determined by the position step. So let's take a look at that. Let's first create a variable that will be called a UV. It's going to be a vec2 UV, and we'll set it equal to vuv.st. Now, for those of you that aren't familiar at all with GLSL, this is a built-in TouchDesigner uniform that will basically return a value from 0, 0 in the lower left to 1, 1 in the upper right. And then we basically will just use that lookup instead of our VUV in our texture function. And this texture function is going to sample whatever input we tell it to sample at whatever coordinates we tell it to sample, which is, in this case, is just the vuv.st coordinates. Now we need to quantize our position before lookup. And so we can do that by using some handy math functions. UV equals, in this case, I will use ceiling, or is it just called ceil? Yep, ceil. UV times, and in this case, let's say times 10. And then we will divide this by 10. And so you want this to be the same number. So this UV times 10 will convert basically our values from 0, 1 to a range of 0 to 10, right? But it'll still be decimals. By taking the ceiling, we then convert those decimals to integers, right? So if I break this out a little bit, we can have it be two separate lines. So this is UV equals the ceil of UV times 10. So this is remap UV to an integer value on range 0 to 10. And maybe instead of 10, I'll have a float and I'll call it step size. And I'll set that equal to 10. And this way, if I use my step size variable here in my code, everything is now procedural and no longer hard-coded. And instead of using 10 in my comment range, I can use step size. Now remap the integer value back to the range 0, 1, and make it a float. So basically here, this is scaling the UV and turning it into an integer, and then we are rescaling the UV back to the range 0, 1 and turning it into a float. But because it's already an integer, a lot of those UV values will end up with the same scaled back to 0, 1 value, right? Because let's say if UV was 0.1, 0.1, and we multiply it by 10, that becomes 1, 1. And then if we divide that by 10 again, it goes back to 0.1, 0.1, right? But if our UV is instead 0.12, 0.12, and we multiply that by 10, it goes to 1.2, 1.2, right? But then we take the ceiling of that, and it's actually 2, 2 instead of 1, 1, right? And then we divide by 10, and so we're back to 0.2, 0.2. If we use, let's say, 1.5, 1.5 times 10, that's, or rather, 0.15, 0.15 times 10, 1.5, 1.5. Take the ceiling of that, it's still 2, 2. And when we divide that by 10 again, we are back to 0.2, 0.2. So any UV value using a step size of 10 with a value between 0.1 and 0.2 is all going to evaluate to the same 0.2, 0.2 scaled lookup. And that is what we're going to use to look up our texture. Scaled lookup value to sample input image. And that is what is leading to this quantization. Now, on the GLSL top itself, you want to go to this input extend mode UV and change it to mirror. That will, for the case where we're on the edge and our scaled value is actually outside the range 0 to 1, we'll just loop around and mirror your input coordinates. You can also set it to repeat if you like, which you see changes slightly. I think mirror is a little bit nicer for our current work. So before we go any further, I want to just do a little refactor and just refactor this into a function that's going to do the same thing. And that is good for two reasons. One, it's a best practice to kind of refactor this logic out to functions. And so this is a good practice in just doing that. And further, it'll let us do the second part of the tutorial, which is going to be using that input map to get the cool wavy look. And to do that, we're going to need this to be refactored into a function. So I'm going to have a function. It's going to return a vec4. I'm going to call that function quantize. And it's going to take in a couple things. It's going to take in an integer value called a texture. It's going to take in a float. That'll be called block size. And it's going to take in, well, just this for now. And basically, we're going to copy and paste some of this code up here. And so the first thing that we want to do is grab the texture coordinates. So we can create a vec2 uv equals vuv.st, and this is just grabbing text coordinates. Now we need to calculate a rounding factor. And so this is going to be basically using this block size that we input. So we'll say vec2 round factor equals vec2, and in this case we'll use our variable that we're passing in called block size. Now we're going to set uv equals ceil uv times round factor, and we will divide then by our round factor, and then we will sample. So this, if I were to comment it, this would be to quantize UV value based on calculated rounding factor. Based on, calculated rounding factor. And maybe actually instead of round factor, we can call this step size, which maybe makes it a little bit clearer and in line with our code below. So now we can sample input texture at the quantized UV coordinate. And to do that, we can create a vec4, we'll call it quantized color equals. And so here we use our texture, std 2D inputs. And here we're actually going to do something clever, and that is use this text variable to actually determine what input we're sampling from, and that will allow us to use our quantize function on any of the inputs, and not just one. And then we can use our UV lookup, and then we can just return this quantized color variable. And that completes our function. Now we can get rid of all of this and actually down here just replace all of that with vec4 color equals quantize. And now here first our texture is going to be 0 because we want to take the first input here, or the 0th input, as our texture to look up from. And our block size can be 10. Now we see that we're returning this, and as I change my block size, we are indeed changing the amount of pixelation here in our image, which is awesome. Now, I want to do a couple things here. First, I want to just give us a uniform value that we can use to control this block size. So to do that, and I guess first, what a uniform value is, for those of you who don't know, is a value that we pass through the shader that can be updated every frame. And every pixel the shader runs on has the same value for that uniform. It is uniform value across all of the pixels the shader operates on. We set that up in our shader code by using the syntax at the beginning, uniform. And in this case, it will be a float type, and we'll call it u step size. Now we go to our shader. We set up a vector on the vector tab with the same name, use step size. And then in our code down here, we can create a float. We can call it step size 2 equals u step size, and replace this 100 with a reference to step size. Now, this is a little bit weird, right? Because we lost all of our images. If we change the step to 50, we get our image back, but we have this position step parameter that's already on the range, what is it, basically 0 to 0.5. So what I really want is to kind of scale this. So I'll drag and drop my position step onto my step size, and then I'm just going to multiply this by 100. And so now, as the step becomes lower, our pixelation becomes larger. And as we drag up to 0.5, we kind of get to this level of pixelation. Now you can, of course, change the ranges here, and by increasing this even further, we get to virtually no pixelation visible. Okay. The last thing, or the next thing rather, that I want to do is aspect correct this. So to aspect correct our quantization, we need to adjust the x and y values that we're using to look this up, because we want to have this blocking quantization happen as a square, like I said at the beginning, not just as a rectangle. And to do that, we need to aspect correct our quantization function here. Now, we need an aspect ratio to do that, and so we can use another TouchDesigner built-in uniform to calculate our resolution. We can have a vec2, call it resolution, and set this equal to utd output info.res.zw. And I'm going to comment this and say UTD output info dot res is a built-in uniform. The XY components contain 1 over resolution of shader, and the ZW components contain the shader output resolution in pixels. So this is a functionally setting vec2 res equal to the output res of shader. We can then use a float, we can call it aspect, and set this equal to resolution.y over resolution.x. And so this will be calculate output aspect ratio. Now, we can pass this into our quantization function by adding another parameter with the name float aspect. We can pass the aspect ratio through our function like so. And now we just have to actually address that aspect ratio up here. And the best way to do that is to actually just scale the step size. We want to have the step size be greater in the x direction than it is in the y direction in this case, because our aspect ratio is less than 1. So instead of having block size be both the x and the y component, we can use block size times aspect for the step size in the y direction. And as you can see, this results in nice square pixels, or pixelated effect, which is exactly what we wanted. And so I'll just comment this out and say sample output color using quantization function defined above. And so this is pretty much the effect. Now, the last thing that I wanted to do was make it a little bit more interesting by allowing an input map to be used that would actually determine the amount of this quantization. Now, the most interesting way to do that, I think, is simply by adding a noise. So why don't I just add a noise using the middle mouse off of this movie file 1. I'm going to change the output to just noise. And because it's an 8-bit float, an 8-bit fixed, if we open the viewer, press N, we can see this is on the range 0 to 1. I'm going to drop a math down afterwards and use the range to rearrange from 0, 1 to 1, 2. I'll open the viewer, I'll turn on normalized. We see this is only 1, 1. The range is from 1 to 1, and that is because we need to set this to a 16-bit float to allow the shader to return values outside of the range 0 to 1, which is what we have because we are scaling this to the range 1, 2. So now we can call this mask, or actually, for best practice, we should have a null after and call this null mask and wire this into the second input of our shader. Now we can sample our mask, and so I'll have a vector, or rather a float. I will set up, I'll use float mask, and then I will set this equal to using the texture function, texture std2d inputs. In this case, I want the first input, which is actually the second input because they start at 0, and I want to look up at vuv.st, and I want just the R component. Now I can use step size times mask to change the step size that we're looking up, which looks a little funky. And the reason is because this is still a very continuous type of texture. And I think it would actually look a little bit better if we quantized this before we looked it up. before we use it as a mask to augment the step size, it's actually quite easy for us to change this. We can just replace this entire lookup with a call to our texture function, a call to our quantize function. So we can use quantize, in this case, looking at the first input, which remember is this text, which is used to determine which input we actually look up from. We can use our regular old step size, and we can use our regular aspect ratio. Now, this is looking a lot more interesting because we have a quantized mask that we're actually using to offset the step size, which determines or leads to this like overlaid blocky look, which I think is now probably time to full screen. I'm going to delete this limit since it was just for an example. And if I drop a speed, and use a constant as the input to the speed here, I'll set this constant to like 0.01, so we have just a little speed going. I'll drag and drop that on my noise transform TZ, and maybe should make it a little faster. And there we have a nicely animated little quantization map going. And the cool thing is, because we are in our code, where's this at? In our code, we're using this as a scale. So we're scaling the step size from step size to double the step size because our mask value goes from 1 to 2. So if we just turn our mask value to be completely 1 by making this amplitude 0, that lookup map effect is just turned off. So I can customize my parent component. I can have a mask weight parameter that I will then drag and drop onto my noise amplitude. And so now I can change how much we're using this lookup and the corresponding animation by using this mask weight parameter, and then maybe also a mask speed parameter, which I can drag and drop onto this constant. And we'll default it to 0.1, and there we are, right back where we started. The last thing I'll do is left click or right click and drop down an in, and I'll name this in text. And so now, if I also, I guess, just drop down an out and go up a level, we have this nice component that will take in any texture and apply this nice quantization effect, which you can change the degree of based on this quantization step parameter. We can also change the mask weight and this animation speed by using these other values. So hopefully that is an interesting technique, and you can learn a little bit about the right ways to set up a GLSL shader, sample textures, and think about doing some simple UV remapping to lead to these interesting effects. That's the end of this tutorial. Thank you all for listening, and I hope to see you next time on the Interactive Immersive HQ to continue our GLSL snippets.
Hey folks, thanks for watching. If you like our YouTube content, I highly recommend you check out the Interactive and Immersive HQ Pro. The HQ Pro is the only comprehensive educational resource and community for immersive design, TouchDesigner, and creative tech pros. In the HQ Pro trainings, we cover almost any topic you can think of, and we go way more in depth than we do in our YouTube tutorials. We have a private group where Matthew Reagan, myself, and our other industry veteran and pioneer teachers answer your questions every single day. If that sounds cool, click the link in the description to learn more. And if you enjoyed this video, hit that like button, and don't forget to subscribe for more free TouchDesigner and immersive content.